Suppose you have this three-dimensional object in front of you. If I asked you to find out its shape, you could easily tell me that it is a cube. Now, imagine that there was another three-dimensional object in front of you that was invisible. How would you determine its shape without touching it? Light travels in straight lines, so when an object blocks that path, a shadow forms, projecting a silhouette. If you collect multiple silhouettes, you can form a collection that reveals the original shape. For example, a sphere projects the same circular outline no matter where you shine the light. In the sciences, we often care about quantities we cannot observe directly. So instead of measuring the quantity itself, we measure several observable variables and construct a model that links those observations to the hidden quantity. This process is known as inverse modeling. Try inverse modeling yourself. We have the following measurements. How can we find the values of A, B, C, and D? In other words, how can we find the values we actually want? Pause the video to try it on your own. Well, we can combine the information we already have and work backwards to find our variables. First, let's define C and D in terms of A. Now, solving for A using the second horizontal measurement, we get A equals 3. We can then substitute A back into the first horizontal measurement, the first vertical measurement, and a diagonal measurement to get B equals 4, C equals 5, and D equals 6. This is how you do inverse modeling mathematically. Let's see how inverse modeling is used in astrophysics. When gravity pulls gas and matter towards the black hole, a spinning disk called an accretion disk forms, emitting X-rays in a rainbow of light called a thermal continuum spectrum. As the disk gets closer to the center, it hits a boundary called the ISCO, the innermost stable circular orbit. This marks the furthest point matter could maintain a stable orbit without falling into the event horizon. Scientists use this boundary to find out a black hole spin through the continuum fitting method. This method needs you to already know the following through telescope data. In inverse modeling terms, these are our observable variables: the distance of the black hole system from Earth, the angle of the accretion disk as seen from Earth, and the mass of the black hole. To measure the ISCO radius, we have to calculate the flux and temperature by fitting the X-ray data from the accretion disk to the following equations using software such as NASA's XSpec. These equations are part of Novikov-Thorne's accretion disk model. Now that we have the mass, distance, effective temperature, and flux, we can finally calculate the ISCO radius using the solid angle equation, which is common to all thin accretion disks. Once we have the ISCO radius, we divide it by our mass because black hole geometry only depends on scale. You want a dimensionless ratio. We match the ratio to our spin based on the Bardeen curve. For example, if our ratio was 2, meaning a smaller radius, our spin would be faster. We can directly observe the relationship between the ISCO radius and spin here. When the accretion disk orbits in the same direction as the black hole spin, frame dragging, which is the twisting of space-time, allows it to stay in a stable orbit close to the event horizon. When orbiting in the opposite direction, however, the gravitational pull of the event horizon is more effective without frame dragging, pushing out the ISCO radius dramatically. Oftentimes, life doesn't give us what we want. Inverse modeling teaches us that we don't need to see the full picture to understand things, we just need the curiosity to connect what we have.